Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problem number 4 of the 2009 AP Calculus AB free response question. This clip focuses on how to compute areas, volumes of solids of revolution, and solids with known cross sections. All right, let's take a look at problem number 4, part A. So for part A, um, we have to find the area of region R. R is the region in the first quadrant enclosed by the graphs y equals 2x, this line, and y equals x squared, the portion of the parabolic function, as shown in the figure above. So what we're going to do here, we're going to be making use of this strategy to determine the area of R. I'm using this strategy because I want to ensure that we do not make any mistakes in the computation of the value of the area. Okay, so first thing we're going to do is sketch the region we are computing the area of, orient and label. Even though you're given a graph, it's always good to sketch it again so you can really label it properly. So there goes our y-axis and then our x-axis. Then let me just make a sketch of the graph. And then we have our line, and then we have the parabolic function like that. Okay, now the point of intersection is given. The point of intersection is 2 comma 4. Let me go ahead and fix that. All right, so I decided to color code the two functions so it's easy for you all to follow what I'm doing here. Okay, so we have the sketch. Now we're going to orient our slice. Okay, we're going to orient the slice that we're going to use to sum up to find the area. Okay, so in this situation, it doesn't really matter how you orient your slice. You are not going to be running into the same function more than once. You have one unique function. Uh, in both directions, if you slice horizontally or vertically, that should be fine. But the functions already as functions of x, so we might as well just slice in the direction of the x-axis, okay? Just for the sake of convenience. So our rectangular slice is going to look something like this, okay? Now, if that's a rectangular slice, the width of the rectangle is going to be dx. That's going to be dx. Um, so all our variables are going to be in terms of x. Okay, so we have the sketch. We've oriented our slice in the direction of the x-axis. Now what we're going to do is label. Okay, so we are orienting ourselves in this direction. Um, we need to label everything in terms of x. Okay, so if we're going in this direction, this function here will be down f down of what? F down of x as a function of x, okay? This is a linear function. This is a parabolic function. We know that this is a parabolic function right here. So that will be x squared. And then the other function, the straight line, that will be what? That will be f top as a function of x, right? Which is equal to 2x. Now, we also need the limits of integration. So the lower bound right here, that will be x left, which is 0. And then the upper bound will be the x coordinate of this point of intersection. Just trace that point down there. And that will be your x right, okay? So that'll be our x right. And that is equal to 2. All right, now we have it labeled. Let me go back to our strategy. So we sketch, orient, and label good. And the next thing to do is to write down the formula, okay? It's always good to write down the formula first before you use it so you avoid making mistakes. So let's write down the formula down here. The formula for finding the area of a region bounded by two curves, area is equal to, now using the notation that's consistent with this situation, we're going to be using functions of x, okay? So everything is going to be in terms of x. So we have the integral from x left all the way to x right have the function on the top as a function of x, okay? The independent variable is very important here, so you have to be careful. Minus the function on the bottom, f down, as a function of x also, f down, and then the whole thing times dx. So that's your dummy variable right there, dx. All right, so there goes the formula that we're going to be using to compute the area of region R. Okay, this region right here. Okay, so we know everything already. We know what x left and x right are. We know what the function on the top is and the function on the bottom or f down. So let's go ahead and compute the area. So area is going to be the integral from 0 to 2 of the function on the top as a function of x, 2x minus the function at the bottom as a function of x, which is x squared dx. Okay, remember you're not allowed to use a calculator in this problem, so we have to do everything by hand. Okay, so let's go ahead and use the power rule to find the antiderivative of these two terms here. Antiderivative of 2x to the first power is 2x to the second power over 2. Apply the power rule. Remember there's a 1 here. Minus x to the third over 3 as the antiderivative of x squared. Applying the power rule again. And then that's the antiderivative evaluated from 0 to 2. Okay, evaluated from 0 to 2. All right, so all we just do is plug in the upper and lower limits into the antiderivative and find the difference. If we plug in the upper limit, oh, this divides out nicely. So plug in 2 there, we have 2 square minus 2 to the third over 3. Okay, that's what you get when you evaluate the antiderivative at the upper limit. Minus, evaluating the antiderivative at the lower limit, you plug in 0 in these two variables, and guess what? You end up with 0. Okay, so that's very convenient. Now let's simplify this. We'll have 2 squared, which is 4, minus 2 to the third, which is 8 over 3. Find the LCD, times this by 3 top and bottom. So we'll have 12 over 3 minus 8 over 3. Final answer for third. So that's the value of the area of region R. The region R is a region between these two curves right here. Okay, so that's that. All right, let's take a look at problem letter B. So it says the region R is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis, that's really important, let's underline that, perpendicular to the x-axis, um, has area A of x equals sine pi over 2x. Find the volume of the solid. So we're going to be using the same strategy again, so we make sure we don't make any mistakes. We're going to sketch, orient our slice, and label. Write down the accurate formula, set up our antiderivative, our expression for the volume, and then evaluate, okay? All right, so anytime you're dealing with solids of um, regions with known cross sections, in most cases, it's going to tell you cross section. Anytime you have that, you will have to tilt the y-axis slightly so you can have a nice visual of what the resulting solid could look like. Okay, so I'm just going to tilt my y-axis slightly, and there goes my x-axis. And then we have a line. Let's make that blue. We have the line y equals 2x. We have the line, and then we have the portion of the parabola. Let's go ahead and sketch that too. So the parabola looks something like that. Okay. All right. So all right, so now that we have this sketch, we have to orient our slice, okay? So in what direction are we going to orient our slice? Well, we have to be really careful to go back to the problem to make sure we're orienting our slice accurately, okay? So in this problem, it says for each solid at each x, the cross section perpendicular to the x-axis. So what does that tell us about the slice? It's going to be perpendicular to the x-axis, so something like that, okay? So that's our slice. Now, since our slice is perpendicular to the x-axis, what does it tell us about the variables that we're going to have um, in our setup? Since it's perpendicular to the x-axis, all our variables will be x's, okay? So we want to express our functions in terms of x, and our limits of integration will be x values, all right? So now this area right here is given by sine pi over 2x, so it's not a regular region like we normally have rectangles or squares or semicircles or triangles. It's some function. So let's just go ahead and create a function. So let's say something irregular like this. Okay, looks like a loaf of bread, but let's say this is what you have. Now this area, this region right here has an area. The area of this region, a of x, is given by sine pi over 2x. Okay, so that's the area of this region, this cross-sectional area. Okay. Now, the function on the top and the function on the bottom, we already know what that is. Function on the top and function on the bottom. Let's just write it again. So f top as a function of what? Function of x. You have to be careful here. Okay. So that's still 2x, and the bottom function, f bottom as a function of x is x squared. We're not really going to use these functions in this problem. I'm just labeling everything. And then we also need to know x left and x right. This is x left, that's 0, as indicated earlier. And then x right, we just trace it down here. X right is the x coordinate of the point of intersection. And in the original problem, that was 2. Okay? That was provided to us earlier. Okay, so we've sketched the graph, we've labeled it. Now what we're going to do is write down the formula. Okay, let's write down the formula that's going to guide our setup. So formula for the area of I'm sorry, the volume of solids with known cross sections is given by V equals the integral. Since we're going perpendicular to the x-axis in this problem, everything will be in terms of x, so x left to x right of the area, the cross-sectional area, a of x dx. So that's how you do it, okay? All right, so let's go ahead and apply this formula to this problem. So our volume is going to be the integral from 0 to 2. A of x is already given to us, so sine pi over 2x. Okay, so sine pi over 2 times x dx. All right, so let's go ahead and evaluate um, this definite integral. So it's going to become, now you have to remember that if you're finding the antiderivative of sine ax dx, it's going to be equal to, using u substitution, you have cosine ax over a. Okay, remember when you differentiate cosine, the sign changes, that's negative sign. So when you integrate sine, you have to reverse the sign of the antiderivative of sine, which is cosine, plus your constant c. Okay, in this problem, a is pi over 2. Okay, so if we find the antiderivative, we'll have negative cosine pi over 2 x, that's cosine ax, divided by a, which is divided by pi over 2. That's the antiderivative evaluated from 0 to 2, applying FTC part 1. Now let's go ahead and make this look pretty. So we'll multiply the numerator by the reciprocal of the denominator. So we have negative 2 over pi. Okay, factor that out, of cosine pi over 2x. Um, this expression evaluated from 0 to 2. All right, so let's go ahead and finish this off. We'll just plug in, evaluate the antiderivative at the upper limit minus the antiderivative evaluated at the lower limit. And we'll multiply our final result by 2 over pi, negative 2 over pi, okay? So let's see what we have here. We're going to have cosine pi over 2 times 2. What is that? That's pi, right? Cosine pi. Cosine pi minus cosine 0. If you plug in 0 into pi over 2x, and then go ahead and evaluate that, we'll have negative 2 over pi. Now, what is cosine pi? What is cosine 0? You already know this, but let's just do a real quick trig review here. So you draw your trig function. We know cosine looks like a cup. So this is pi over 2, and that's pi. So cosine looks something like this through there and down this way. Okay, so you can clearly see that cosine pi is cosine, this is pi right here. Cosine pi is negative 1. This is negative 1, and cosine 0 is 1. Okay? Okay, so we're going to have cosine pi is negative 1. Cosine 0 is 1 minus 1. So we have negative 2 over pi times negative 2. And our final answer is 4 over pi. Okay? So that's the volume of the resulting solid. All right, let's take a look at the C part. Part C reads, another solid has the same base R, so this bounded region R right here is what we're talking about. For this solid, the cross sections perpendicular to the y-axis, let's underline that because that's very important, perpendicular to the y-axis are squares. Write but do not evaluate an integral expression for the volume of the solid. Okay, so we're going to be using our strategy again, but we're not going to evaluate. We just stop at the setup, okay? So first thing you want to do again is sketch, orient, and label. Since we're dealing with volumes of solids with cross sections, that's the key word. If you see the word cross section, you want to tilt your axis like I did over here. This is your y-axis. That's your x-axis. All right, so sketch it like this is easier to give yourself a visual of the situation. Now we're done sketching. Next thing to do is to orient our slice. So how do we orient it? Is it going to be top down or side to side? We are perpendicular to the y-axis. Okay, so our slice will be perpendicular to the y-axis. It's going to look something like this. Okay, so since we're perpendicular to the y-axis, what does that mean concerning our label? Everything is going to be in terms of y. Okay, so we're going to have to label this function. The function on the top is going to be as a function of y, f top as a function of y. The function on the bottom will also be a function of y, f bottom as a function of y. And then, of course, the area will be a function of y. But what kind of area do we have here? What kind of shape are we computing the area of? We're computing the area of a square. Okay, so let's draw a square like that. So that will be our A of X region. Okay, so there goes the region right here. So this area, this rectangular region, this is going to be A as a function of Y. All right, so let's call this L and call that L. So we know what the area is going to be. It's going to be length times width. All right, so now we have it. Oh wait, we're not done labeling. Since we're going in the y direction, we are going to need x. I'm sorry, y down or bottom. Y on the bottom. Let's call it y down. That's going to be 0 all the way to the top. Okay, so trace it is going to be somewhere there. So back it back there. So y at the top, that's going to be the y coordinate of the point of intersection. Um, what was that? I think it was a 4. Yeah, so that's what we had in the original problem. It was 4 because if you square 2, you get 4. Okay, so that's a 4 right there. All right, now, so let's go ahead and write down the formula. We've already labeled it, everything that we need. The formula is going to be in terms of y, okay? So let's write down the formula. It's the same formula as we use in part B. So formula for the volume of solids with known cross sections is equal to the integral from y down to y top, okay, of the area as a function of what? Area as a function of y, because we're perpendicular to y-axis, everything is all y, okay? So dy is your dummy variable. All right, so let's go ahead and set it up, apply this formula to this problem. So our volume V is going to be the integral from 0 to 4 of the area as a function of y dy. Okay? All right, we're not done with the setup yet. We need to figure out what a of y is. So a the area as a function of L is L times L, right? Length times length, which is length square. Okay, so that's the area as a function of L. But in this problem, we need to write the area as a function of y. Okay, so to find the length of this side L, we have to subtract f top as a function of y minus f bottom. Actually, you subtract f bottom, f top, yes, from f bottom. That's how we're going to do it. All right, so let's go ahead and do that. We're going to have, let's see, we know that this function right here was provided as a function of x, which is x squared. That was y. And the other one was provided as a function of x also. A function of x, that was 2x. Now, what are we going to do? We're going to have to solve these functions for x, okay? So let's start with the one on top. So this is y. So from the one on the top, we know that 2x is equal to y. So to get x by itself is easy. We just have x is equal to y over 2. So this is the function of y for the function at the bottom. And then for the other function, we have x squared is equal to y. To solve for y for x, we simply take the square root of both sides, and we have x equals the square root of y, and that's our function of y. Okay, so what is L going to be? We have to be really careful here. So what is L going to be? So for L, we're going to subtract this. If you're standing on the y-axis and this is your x direction, to get the length, you subtract this function here, the function on the top from the y direction, but is on the bottom from the x direction. You're going to subtract, this is the function on the top, that's the function on the bottom. So you subtract the smaller function from the bigger function, okay? So just to make it clear, let me switch my labels. So if I'm going from the y direction, this should actually be the top. In terms of as a function of x, as a function of y, this should be the top function. And as a function of x, it should be the bottom. Okay, so it kind of switches around depending on how you look at it. And then from the y direction, that function closer to the y-axis is the function on the bottom, or f down. So what's L going to be? L is going to be the blue one, I'm sorry, the green one, the bigger function minus the smaller function. So L is going to be um, f top, f top minus f bottom. Okay, f top as a function of x of y minus f bottom as a function of y. I just want to write this so that we all know what's going on. F down as a function of y, and then we just simply plug in the two values of the functions, and that will be our final answer. Okay, f down as a function of y. Okay, so let's see what we have. So L is going to be um, square root of x minus y over 2. Okay, so If this is the length, then what is our area as a function of L? Instead of L squared, our area as a function of X, I meant to say, A as a function of X, we just simply substitute this quantity, no, area as a function of Y. I'm getting my variables confused now. So this is Y. So the square root of Y. Area as a function of Y is equal to L squared. So it's just root Y minus Y over 2 quantity square. All right, so that's our area as a function of Y. Now let's go ahead and plug that into this expression right here. So that yields the volume is equal to the integral from 0 to 4 of square root of Y minus Y over 2. That's the side length of the rectangle of the square, the whole thing squared, dy. Okay, so there goes your final result. Thanks so much for taking the time to watch this presentation. Really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. If you have any questions or comments, include it in the comment section below and we'll address it as soon as possible. More clips can be found on math.serve.com under AP Calculus. Thanks again for watching and have a wonderful day.